Hello dear colleagues and other enthusiasts who are interested in radio wave propagation. Happy Christmas holidays to everyone, and today before Christmas we're going to finish our big section on the propagation of radio signals. And then after Christmas we are going to start with antennas. Before proceeding to this last chapter of this section, please let me take a look at the quiz results from the previous time, from the previous subject about refraction and abnormal propagation. So here are the results. The first question was answered regarding the group or signal velocity of a radio signal, whether or not it can exceed the speed of light in vacuum. And most of you answered correctly that no, because this is the velocity of the information, of the energy transmitted. It cannot exceed the speed of light in vacuum. But the phase velocity can do that, as we learned, under some circumstances. For example, in the ionosphere of the Earth. Then the question was asked regarding how to explain the radio beam bending, and most of you answered correctly, that the upper part of the radio wave front travels faster than the lower part, and this is because there are differences in the refractive index of the atmosphere, because atmosphere is not homogeneous and the refractive index varies with the altitude, so it results in the beam bending downwards. Which physical parameters define the velocity of propagation? And almost all of you answered correctly that these two are relative permittivity and relative permeability. Of course, it has nothing to do with the speed of light in vacuum itself and any angles of incidence, for example. So, for this question, both answers are correct. So with increasing the altitude, what happens in atmosphere is the pressure, temperature and humidity decrease, while the radiofrequency decrease exponentially. In this question, one of my colleagues noticed a mistake, yes, and it was about the third option, which was it was meant the standard refraction, not the one that you see on your screen, but it wasn't a hook, it wasn't a trick, it's just mistyping. And also there was a technical problem with selecting answers. Initially it wasn't possible to select more than one answer, but actually here are two correct answers. So later I fixed that, and also in the today's quiz test, I allowed to select as much answers as you like. So now all questions are multiple choice answers, and there could be more than one answer. But the abnormal is considered subrefraction, superrefraction. The next question was regarding the effective Earth radius, or K factor, and almost most of you answered correctly that it is the representation of signal propagation conditions making its trajectory linear. The last question divided the opinions in quite broad way, and was asked about the refractivity gradient and why does it matter. And actually all of these points are correct. So this is a universal parameter which measures the refractivity variation with altitude. It also is the way of defining the propagation trajectory of radio signal, and also we can evaluate whether the propagation is abnormal. So all of these are correct. All right, now let us get to the last chapter. And this chapter will be dedicated to the multipath and also different types of propagation. Speaking about multipath, this phenomenon is a serious headache for link planners, for microwave engineers, because it brings a lot of troubles. And we are going to learn why and how it happens. And of course, we are going to concentrate first of all on the basic physics of this phenomenon. How does it initiate? What are the conditions? And then we're going to take a look at possible communication problems which it brings. So from the perspective of radio engineers, of microwave engineers and link planners. So, as the multipath term is closely related to diffraction and to interference, let us examine first what is wave interference at all. So what is interference? What do you remember from your physics school, from your physics lessons in school? I like this moving diagram because it gives us a basic understanding of what interference is. Here are two signals represented by the green curve and by the blue curve shown together. Their phase difference is varying with time, which results in superimposed signal marked in red as a red curve. And we can see how this overall signal changes from zero, from the absence of signal to the maximum, to the peak with the largest amplitude possible. And if we are speaking about some perfect conditions, about some mathematically correct definition of interference, about some theoretical abstraction, let's say, then there is a requirement for these interfering waves. We're speaking about two or more interfering waves, and now we're speaking about some ideal signal, imaginary signal, and this requirement is called coherence. So two or more signals must be coherent in order to interfere with each other. What does it mean? The coherence requirement assumes three different conditions to be fulfilled. The first one is identical frequency. As we can see on this picture, the frequency of two signals is identical, of this green curve and blue curve. Also, they have the same identical waveform. So this is our second requirement, second condition to be fulfilled. And for steady interfering pattern to be observed, we also have to preserve the constant phase difference. In this example, the phase difference is changing all the time, the phase shift is changing, and thus we observe different resulting of the interference. We observe different amplitude of this overall signal represented by red line, red curve. However, for some particular condition, this phase should be different, and it must remain for some longer period of time to be observed. Now, the interference can be either constructive or destructive if we are talking about this perfect mathematical model. The constructive interference assumes that the phase difference is an even multiple of p, or 180 degrees. So this phase shift, phase difference for perfectly constructive case must be either 180 or multiples of this number. So it can be 340, 360, it can be 0 degrees shift, which is the same thing. So multiples of p, this is what makes the interference constructive. And on contrary, it can be destructive if the phase difference is an odd multiple of p. So 1p, 3p, 5p, etc. So it can be either, let's say, P itself, 180. Sorry, the previous case would be constructive if there would be 0p, 2p, 4p. So 0 degrees shift, 360 degrees shift, etc. And the destructive case happens when there is an odd multiple of p. So it would be the p itself, 180 degrees, 270 degrees, etc. Actually, 270 would be something in between. It would be intermediate case. So here we are speaking about the whole numbers of p. So 3p, 5p, etc. But these cases are quite rare when there is a just exact difference of multiples of p number. But most of the time we are dealing with some intermediate cases, like you can see on this picture. The phase shift is varying all the time, and we most of the time have these intermediate states of some certain phase shift. It can be 90 degrees, 100 degrees, 270 degrees, 300 degrees, etc. And if we apply this model to real life, to the communication channel between the signals, then of course we have to understand that the frequencies could be not perfectly identical between the signals. The waveform can vary to a certain extent, and the phase difference can be changing over the period of time. Nevertheless, we still observe some degree of this interference. It cannot be considered as the perfect interference case, like in this mathematical or geometrical model, but still this is interference. This is what we call interference in terms of radio communications. So this coherence requirement is true for this perfect mathematical case. However, in real life we are dealing with deviations from these rules, from these requirements, and we were not getting a perfectly even signal all the time, and we almost always get these intermediate cases of interference, something in between. This also applies to real-world conditions. Let us pause this picture. Sorry. I guess I have to do this from another view. I have to bring it on like this, and now I can take a pause, like here. And what do we see now? For example, let's freeze this moving picture at this point of time. Here we see the destructive interference. It's not perfectly destructive. It's not the resulting signal, the red curve doesn't disappear completely, but it is suppressed. The resulting waveform has lower amplitude than the initial two signals. This is because we have the phase difference, which results in this condition. This phase difference is something between 19 and 180 degrees. And here we can see the complete destruction, let's say, of both signals. They annihilate each other, and the degrees, there are 180 degrees phase shift, which results in complete absence of the resulting signal. And on contrary, this is something close to the perfectly constructive condition, when both signals superimpose and they result in larger signal amplitude. Although this is not a perfect constructive case, because we can see still some minor phase shift between these two signals. If they would coincide, that would mean that the phase shift is either 0 or 360 degrees, and in that case the amplification would be at maximum. All right. Now we can go a bit further and ask ourselves again, what is interference? Previously I showed you this perfect mathematical case. Now let's get a bit closer to the practice, to the practical cases. So as I mentioned, interference is closely related to diffraction and to the multipath, as we will see. What is diffraction? Does anyone have any idea of what does this picture represent? You can share your thoughts. It is related to the diffraction phenomenon. Maybe somebody has heard something about this. And what specifically does it represent? It is clear that in some sense it shows the diffraction phenomenon, but what is that? So I will wait for your suggestions. You can just shortly name it if you wish. If you know the exact name of this experiment or some approximate. Yes, this is the diffraction pattern which we can see on the right of the shadows and half shadows and lighter regions and shadowy regions. Light through apertures, correct. Yes, that's also correct. But to be specific, this picture represents so-called double slit experiment, which had been conducted. Yes, correct. Conducted by Thomas Young in 1902. And at that time, this experiment showed the wave nature of light. So this experiment was demonstrated demonstrated wave behavior of the visible light. But later, more than a century later, the same experiment was repeated with the electrons. And it demonstrated that electrons also show this wave behavior. So later it was repeated even with atoms and with molecules. And this experiment showed that actually any matter or any particle or any wave exhibit both the parameters of the wave and of particles. So this experiment proved a wave-particle duality of any object, of any matter, particle or wave. And this experiment showed the diffraction phenomenon. Also, the Fresnel zones concept is related to diffraction and to interference, as we learned. So, if you remember, we saw that there are multiple secondary sources, Huygens sources, which are divided in these large zones around the line of sight, and all of them contribute to the received signal level. How? By means of interfering with each other. They are all producing the secondary waves which interfere either constructively or destructively at the receiver side, and they produce some signal strength as a result. And when some of them are abstracted, we observe deviation to one side or to another. We can either amplify our resulting signal, or we can attenuate. And this phenomenon is also related to the multipath, because as I showed you with a single object abstraction in the middle, when there are reflections either from the ground or from the single abstracted element, like the flat roof of the building, for example. So when we see that this Fresnel zones concept is related to these reflections, we are talking already about multipath. And multipath, it's nothing else but multiple wave propagation, the signal propagation over the multiple paths. So we not only have this primary path between A and B, but we also have these reflections from some objects on the Earth or from the Earth itself. We have refracted signal from different layers of atmosphere. And all these different secondary signals combine at the receiver and cause interference with the primary signal. And this is basically what multipath is about. So let us take a look further about what is it. So as I said, we can define it as the superimposition of direct ray and any reflected and refracted rays. And in practice, these are multiple rays, more than two, of course, and they can be the result of either reflection from water surface, from ground, from some flat objects, for example, from the rooftop, or they can be refracted from different layers of atmosphere, from ionosphere, and due to some abnormal propagation, due to some unusual variations of the refractive index of the atmosphere. So, but there are primarily main two sources, which are reflections and refractions. So here we're not speaking about the Fresnel zone concept, where there are multiple sources, all of them produce secondary waves, and all of these waves are combined together. This is considered to be like normal propagation. And this is what happens anywhere in space, in vacuum. If we're talking about multipath, we're talking about these reflections and refractions. And they assume that we have some medium where the wave propagates. Thus, it is refracted from somewhere else. And also, we assume that it propagates over some terrain, like in case of radio communications. So it is reflected also. And both cases are shown on this picture. You can see the reflections from the water surface, this dotted line beneath the main beam, and above the main beam there is a refracted ray of signal. And we will see that this is sometimes called ducting effect or duct, when the signal, the secondary signal, which normally propagates in this direction naturally, but in this case it gets trapped inside some layer of the atmosphere and sent back to the receiver. And there it is superimposed on the main beam, and there some kind of the interference pattern is produced, which either amplifies signal or attenuates it. So yeah, and we have two outcomes, the amplification or attenuation of a radio signal. Of course, intuitively we assume that attenuation is easier to get, and it is mostly observed over the radio links. That is why we consider multipath a bad thing. Because for amplification we need to maintain some, let's say, perfect conditions when the phase of these two signals coincide perfectly and the signal is amplified. However, most often there are different disturbances. The path over which the secondary beams travel varies in length, so the phase shift is always changing and the polarization changes, etc., etc. The atmospheric conditions change, so it's very difficult to preserve this amplification effect. But most of the time we either attenuate signal or we distort our signal. And this is how it looks like in time. On the x-axis there is a time scale, on the y-axis there is a received power. And we can see that if the multipath conditions are heavily negative, if they are unfavorable, then we observe this path, this pattern of constant changing signal. There is a middle point somewhere in between these extreme states. Yeah, when you can see this slashed line, this is like the normal received signal level without any disturbances, without any multipath effect. But the actual multipath gives us this changing signal strength all the time. And these notches, these attenuations are much more pronounced than amplification cases. You can see that our signal is attenuated, and due to this our noise level increased, signal to noise level degrades, and we sacrifice the quality of signal because of this effect. So this is a negative effect for the radio engineers. And it results in two kinds of fading, or in selective fading and non-selective fading. Selective fading, we will learn about this a bit later, but it's worth mentioning that it is especially dangerous for wideband digital systems because it produces disturbances in the band of the signal. So wideband signals suffer from it more. In turn, non-selective fading is more effective for these narrow band analog systems, some older communication systems. Of course, non-selective fading also affects the wideband systems, but it would be sufficient to increase our fade margin, to increase our signal level to overcome this effect of non-selective fading. However, for selective fading, we have to invent some new strategies of how to fight multipath, because it's not enough to just increase fade margin to increase our signal, as we cut part of our spectrum with the selective fading. Alright, so let's continue. And let's continue with some mathematical analysis. It won't be a difficult one, but it will give us like a simplified view on what's happening with the signal from the mathematical or geometrical point of view. Sometimes in some books which describe multipath phenomenon, we can see this two-ray multipath analysis. They could be three-ray multipath analysis, etc. This is a simplified model of how we can evaluate the multipath effect depending on different initial conditions. And for such evaluation, we have to define our input. That would be two signals. Our direct ray signal, denoted by V direct, and you can see it's a cosinus of omega 0 t, so with a certain phase. And the reflected ray, which actually is a replica of the direct ray, but multiplied with this raw coefficient and with the phase shift of phi1. So rho 1 represents this difference in amplitude between the main signal and the reflected signal. If this is 0, then we don't have any reflected signal at all. If it reaches unity, then the reflected signal is as strong as the main signal. So they are equally strong. And in real life, this value is somewhere in between 0 and 1. So we will see different conditions on this graph on the right. And phi1 represents the phase shift, as we observed on the initial slide, with these two blue and green curves, which change the position all the time and vary their phase shift. And the result was different all the time. This resulting red curve varied along with this phase shift. And here we also use this phase shift as an input value, and we assume that it can be different. So in order to obtain our resulting signal, which we receive at the end, at the receiving point, we have to find the complete signal. We have to sum together this direct ray signal and this reflected ray. So in order to obtain the received signal level. And we can describe this complete signal by this beta squared, which is the ratio of this complete signal power to the initial direct ray power. So this is a kind of a method of how can we evaluate whether the complete signal is amplified or is it attenuated. So this ratio, we evaluate this ratio between this complete signal and this initial signal. And we can see that this value here on the right reaches different values. It can go as low as -40 decibels, or it can be maximum 6 decibels. Do you remember that we had this diagram previously which showed that the clearance conditions, which show what different Fresnel zones conditions, and we saw that the most favorable case was when there was the first Fresnel zone clearance, and there we could obtain up to 6 decibels of signal amplification. But in that case, we assume that the reflecting surface is perfect reflector, and the reflected signal has the same strength, the same amplitude as the direct ray. And in this case, we will have this maximum 6 degrees. In all other cases, we will have less. But this is the perfect case. So let us take a look at this graph and at the case when we have ρ1 equal to unity. That would mean that the reflected signal has the same amplitude as the direct signal. This is the perfect conditions never achieved in real life, but let's assume that we can get close to this in real life, let's say, but never reach this mark. In that case, we can see this solid curve, and it all depends on the phase shift. When phase shift is an odd multiple of p, or 180 degrees, for example, then we would observe perfectly destructive interference. Like in this case, we can see that the phase shift is 180, and we have this notch of -40 dB here. That would mean that our received signal will be decreased by 40 decibels. And on contrary, we would have the perfectly constructive case if the signal would reach here, if the phase shift would be either 0 or 360 here. We can see that there is a 6 decibels improvement in this case. And if we assume that this reflected signal is attenuated or scattered or diffracted somehow, then we would assume that the effect of this multipath will be less. And this is what the other curves represent. If this amplitude of the reflected ray is less than unity, then we have this not so pronounced notch here in case of destructive interference, and also not so pronounced amplification in case of constructive. And of course, we'll have a lot of intermediate cases in between these extremes, between perfectly destructive and perfectly constructive. And this is what we see most of the time in the real life for the real links. Again, this results in either amplification or attenuation. And here is one interesting analogy, which I came across some time ago. And this is how we can represent the multipath. Actually, we can represent it as a FIR filter. If you know what is it, if you don't know, that let me explain. In signal processing, FIR filter is a finite impulse response filter. This is just like a filtering element in electronics. It can be either analog or discrete, digital, sorry. This is the filter. This is a way of how we are filtering our signal, right? And it is called finite impulse because when it obtains an impulse on the input, the response will be finite in time. So the impulse will settle down with some certain finite amount of time. And this is in the contrast with the IIR, or infinite impulse response filter. So let's say we have this element. What does the usual digital filter do? Like if we consider it as an element in electronics. This is a question to you. What do we achieve with a simple filtering element in our electronics? For example, it could be in a radio tract, in a receiver, in transmitter, in signal processing. What does the filtering do? Why do we need these filters? This finite impulse response filter or any other filter at all? While you are thinking, I'm going to go to the board and draw some pictures to explain you this concept. Let's say we have a graph like this, and here we have a magnitude of some signal expressed in decibels. And here we have a frequency, let's say in megahertz. This is the usual suppress unnecessary signals, one of the answers. Passband, low pass filter, high pass filter. Yes, that's correct answers. So with a filter, we're just filtering some bands of the signal. We are filtering out the low part of our frequency spectrum or our high part of frequency spectrum, or we filter out some signal in between. So we can call it either low pass filter, high pass filter, or pass band filter, or stop band filter. In this case, we're referring to this finite impulse response filter as to stop bands filter. So we are filtering out some part of the spectrum. Let me show you this typical curve representing the filter characteristic. So here we have what is called the unchanged signal level here, the attenuated signal here, and the stop band in here. So actually we are filtering out this part of the spectrum between these two frequencies. And this is called the stop band, and these two parts are the pass bands, right? We are passing this signal through the filter, but we're filtering out this one. It can be used for different purposes in electronics. It can be filtering out some unwanted signal, unwanted spurs of the signal, anything else. So multiple of applications for this component. But this is just a simple example of what does this filter do actually. What is its purpose? Okay, and once we get that clear, let me show you the structure of the filter itself. If we represent it consisting of some functional blocks as a functional diagram. So we have some signal on the input, x, depending on this order. And we have, this is our input, and we have some output. Let's say y function. And what happens in between? Let's say we have our initial signal here, and we have to filter out this part and obtain this y function, this y signal here. So what do we do if we want to use our finite impulse response filter? We add multiple replicas of initial signal which are shifted in time. So we have to shift our signal in time, but by some certain amount of time. And this block will do this job. It will just delay our main signal, but by some amount of time. And we have the initial signal here going through another functional block represented by some coefficient. So this is what we call the impulse response, or a coefficient, if we need to multiply our initial signal by some expression. Here we have our delayed signal, which again goes through some certain reworking process, some processing, right? And here is another functional block when we add these two together. So we sum them up together, undelayed signal with a delayed signal. And we repeat this pattern further. Again, we introduce another shift in time, another delay. Again, we process it through some coefficient, and we add up these two signals, etc. And the output, so this can continue or it can stop. This is just an example, so let's stop here. We have just 1, 2, 3. We have one main signal and two delayed signals, so two replicas. And actually, this is what is happening in nature. This is what is happening with radio waves, because we have our main signal all the time, and we have some multiple replicas. We have different secondary signals which are either reflected from the surface of water or terrain, and we can have also some refracted signals which take a different path to get to this receiver. And all of these secondary reflected or refracted signals are shifted in time. They are delayed because they have a little bit further to travel to the receiver than the direct path. Because direct path is the minimum path that we can draw between point A and point B, right? This is the shortest path. All other would be larger, will be longer. So the signal is delayed here. And this coefficient represents actually of how the amplitude of the refracted signal changes. It can be unity, then we have the same amplitude as the main signal, or it can be less than unity, right? Then the effect will be also less. In the two-ray model, we have just the main ray, main signal, and slightly delayed signal. In some more sophisticated models, we can have 3 of them. It is called 3-ray model in this case. And we have, in real life, we have an infinite number of these reflections, refractions from all over the place. But most of them do not contribute to the overall signal because they are too weak. Because this coefficient is very small for them, so they don't change anything. And this is how we can explain the selective fading of the radio link. Because this whole system represents the FIR filter, and we cut out part of our spectrum, like this, just because of natural conditions. We are producing our own finite impulse response filter in nature, which cuts the part of our spectrum. And this is the bad thing about it, right? So we have to get rid of it. So let's get back to the presentation itself. And if we continue using this analogy with the finite impulse response filter, then we will have something that looks like this. This concerns the two-ray model, so the simplified model, when we have just one direct wave and one reflected wave. But what do we see here? First of all, on the left there is the same attenuation, right? So the maximum of 6 decibels and the minimum of -20. But here on this x-axis we have the frequency spectrum. The same as I showed you on the board. We had this frequency and we cut out the middle part with our filter, right? So here we can see the same. We cut the part of the spectrum here. And this notch can be, for example, in this case, at about 4.5 gigahertz, right? So we cut the part of our spectrum. And this largely depends on the refracted signal delay. So here are 4 examples of different delays in nanoseconds. And you can see that by increasing this delay, we actually obtain wider cut. So we extend this pattern. If the delay is small, then the notches become more frequent, and we cut our spectrum in different places. But for the radio communications, we're just concerned about cutting our bandwidth, our transmitting channel. So this is what is called selective fading, and how it can be explained by the analogy with a finite impulse response filter. The non-selective fading sometimes is called flat fading as well. And here what is meant by the selective fading. We can see two pictures, one over the other. The first one, which is unchanged, this upper picture, this upper curve, is our undisturbed signal, our normal signal. And this is the bandwidth of the signal, the part of spectrum occupied by the actual information. This is how we transmit the information itself in this channel, modulated by some signal. And under the multipath conditions, under the selective multipath conditions, we can observe something like this. We can have this notch because our environment serves as the finite impulse response filter virtually. So it cuts out the part of the spectrum because we have this superimposition of secondary signals. And of course this disturbs the signal, and this brings in noise, and this decreases the quality of the signal. Also, it causes so-called inter-symbol interference, which is very important for the digital signal, and it results in the condition when we cannot distinguish between different digital symbols. When the binary information is transmitted and modulated over the signal, disturbed, it becomes distorted, and we cannot distinguish between different symbols which are transmitted with a modulation. So this is very dangerous for the digital communications, and as we know, almost most of the modern communications are digital wideband communications, like in the case of microwave industry. Now we have almost all these communications based on this wide digital signal. This is why multipath is so concerning, especially for the wider channels, like 112 megahertz. And what are the variables that matter? What are the variables which on which the multipath effect depends? So from the point of view of the signal, these are signal delay, which sometimes in some formulas represented by tau letter, or this can be represented as a phase shift between the primary and the secondary signal. And indirect signal amplitude. This was represented by ρ in our previous example in two-ray analysis. And also we have to take into account of how the secondary signal propagates. So if we have, let's say, abnormal propagation, then the refraction will be much stronger, and we will have more superimposed secondary signals over our main signal. And this is dependent on the atmosphere itself and on some climatic conditions. So what matters is the set of parameters which describe the atmosphere. These are refractivity gradient, also terrain roughness, because we can have perfectly reflecting surface, or we can have surface which scatters signals all over the place, and thus we will have less reflections, direct reflections. So that is why links over the water exhibits more multipath effect and more problems due to multipath fading. Also, path inclination is what matters, because this defines the geometry of the link as well as antenna heights. And the multipath effect is also dependent on the frequency. Especially for the lower frequencies, it is more pronounced, and it is more dangerous for frequencies under 10 gigahertz. Of course, above 10 gigahertz, we can also experience multipath, but below this value, it is believed to have much more effect on the performance. And the other types of fading, which are related to multipath, but may be present during a smaller percentage of time and may be much more dangerous than the usual multipath, are the following. The first is ducting. As I said, ducting is this effect of very strongly refracted signal which gets trapped in the certain layer of atmosphere. So it is refracted downwards, very extensively, then it is reflected back from the Earth, refracted again, and thus it travels in a kind of a duct or of a tube. That is why it's called ducting, because it gets trapped in particular part of the atmosphere, and it is causing reflections, a lot of reflections to the receiver, because we not only have this primary signal, we also have a lot of the secondary signals which are going up and down, and all of them get received at the receiver. And the ducting can be elevated when the same happens not just above the Earth, but somewhere in the upper layer of the atmosphere. In this case, the signal is refracted downwards and then reaches some altitude, it is getting back upwards, and thus it travels. And very strong ducting condition can even cause blackout, which is when we have such strong abnormal refraction or super refraction that we lose our signal completely. Again, another extreme case of this phenomena is beam spreading, like shown in this picture, when we have when the different part of the wavefront take different paths, and one part of the wavefront is refracted upwards, the other part refracted downwards, which causes this defocusing of the radio signal, of the radio front. And this is what produces so-called radio holes, when there is a significantly lower signal, received signal level, and thus we can lose our signal completely if the receiver gets into these radio holes. Also, there are some other effects, for example, scintillation, which is observable for some higher frequencies over 40 gigahertz, but due to some turbulences in the air, but this is not so pronounced, and usually it doesn't result in any significant signal degradation. What are the countermeasures for the radio engineers, for the link planners? So the most popular and most effective is the space diversity. It preserves the link from both flat and selective fading. So it is extremely useful for both analog systems and digital systems, wideband systems. This is how it looks like. We have two antennas at the receiving side, and each of these antennas have its own signal path. So marked in blue and in green, in this case, right? And each of these antenna has both direct signal and reflected signal. And while one of the antennas may have the destructive interference case, the other antenna is placed in such a manner that at the same time it would have constructive interference case or no interference, like no effect from the interference, from the reflection, sorry, from the multipath. So we select this high difference between the two antennas in order to maintain that there is always a usable signal on one of them. If we have a notch, like if we have destructive multipath at one of the antennas, then this path difference between these two rays is selected accordingly in order to have no effect or positive effect on the other antenna. And the end system, our modem, selects from these two signals. And then situation can change, just the opposite way. Because atmospheric conditions change. If there is a water, the water level can change, etc. So we can then receive better signal on one antenna than on another. And then we can change the situation. And modem must select between these two. And it selects the stronger signal, the less affected signal. And this is how the space diversity works. We also have frequency diversity, which would be at the second place by the popularity. It preserves link from the selective fading, because we have two different frequencies. And what is selective fading? Selective fading is when just one frequency is affected. We have this notch in the particular stop band, while the other is not affected. So we have reserve, redundancy. And again, with the time, the situation can change. We can have the attenuation in the other band. So we will have a modem to select between these two signals. This is what represented here in this picture. We have the frequency diversity system with the two signals which is attenuated at different times. So we always have some positive signal, unaffected signal at the same time. And we choose from these two. There are another ways of redundancy of protecting the link against multipath, like angle diversity or combined diversities of all these three kinds: space, frequency, angle diversity. They can be combined together for increasing their effectiveness. As well as we have some non-diversity methods available. For example, we can use the nature obstacles in order to block the received signal from the terrain, the reflected signal. We can hide our receiver behind the mountain, for example, or a roof of the building, in order to pass the direct signal but to block the reflected signal. So these are some non-diversity methods. And if we are talking about built-in techniques, that we use equalizer in order to get rid of these notches inside our spectrum. Equalizer is what equalizes, makes the whole spectrum even. So using especially digital taps inside it. So this is a digital technology which tries to make the spectrum even. So to equalize this faded parts of the spectrum in order to restore signal quality. Alright, so enough about multipath. Let's speak a little bit about different types of propagation. And this will conclude our propagation subject. We're going to review different types of propagation, and I hope this will be not as boring as the first part with these mathematical models and stuff. This will be a bit more entertaining because I'm going to present some examples. And these would be not usual cases of propagation. But let's start with the usual case. Let's start with the so-called line of sight propagation, which is mostly used for microwave communications. What is line of sight propagation? Usually we are speaking about the frequency of more than 3 MHz or even more than 300 MHz and up to 80, 100 GHz, etc. Usually we want the Fresnel zone to be clear from obstructions in that case. We're talking about the first Fresnel zone clearance, of course. And usually this is where we observe this multipath effect. But most of the time we were speaking about things which are related to this line of sight propagation, starting from the discussion about free space loss and then going further to this Fresnel zone concept, and now about this multipath and diffraction. So more or less we have some basic understanding of how these signals propagate as line of sight signals. That is why let us take a look at different other types of propagation. The other type is non-line of sight. When we don't have line of sight or line drawn between the transmitter and receiver, so no visibility, no direct visibility. What can be the result of this propagation? Of course, the diffracted signal. We learned that the signal will get through this, right? It is diffracted. It is not necessary to have the direct visibility between 2 points in order to communicate. We can communicate through the wall. Radio waves propagate through the wall, through the mountains, through the buildings. So we can have some blockage, but still get the signal at the other side of the link. But of course, we are going to sacrifice some power of the signal, but the diffracted signal will get through. In order to overcome some very important obstructions, we can have different passive repeaters. For example, the reflective panels which are shown here. And this is how we can bounce the signal 2 times in order to get over the mountain, for example. If we cannot establish a direct visibility, then we transmit our signal to one of these panels. It bounces from this panel, gets to the other panel, bounces from the second one, and gets further on the other side of the mountain, and then it is received there. This is called passive repeaters because we are not regenerating signal, we're not retranslating it. Also, the back-to-back antennas, by the way, the same thing, but without the panels, just with one antenna connected directly to another antenna. And one is receiving and transmitting the signal further. Also, we can have the active repeaters, like shown here. Actually, here we can assume both passive repeaters as back-to-back antennas and active repeaters. But the active repeater is when we received signal with the antenna and retransmit it with another transmitter to the other side of the mountain, let's say. And this is how we can overcome this non-line of sight propagation. But this mostly concerns some FM radio range and microwave radio range. So VHF communications and UHF, SHF communications. Let's take a look at something more interesting. For example, at the ground waves. What are the ground waves? So we can call a ground wave the wave which first of all is less than 3 MHz in frequency. And we can, this category includes ELF, SLF, or ULF, etc. Frequencies, which are medium waves, long waves, very long waves, medium frequency, high frequency, very low frequency, ultra low frequency, super low frequency, and extra low frequency. And this corresponds to the long waves, medium waves, short waves, and some even the waves with even lower frequencies. And why do we call them ground waves? It is because they are very strongly diffracted and they follow the Earth's curvature, so that the dimensions of these waves are kilometers long. And that is why they are very similar to these Earth curvature elements, to some mountains, hills, larger buildings. The same size of the waves, comparing to the obstructions, make them diffract effectively over these obstacles. So they can pass over these obstacles without significant loss of power. And thus they can be transmitted further. We can prolong our line of sight considerably by using ground waves, which is an interesting phenomenon. And also, we can consider ground as a lossy dielectric here. And the propagation of ground waves is very much dependent on the type of the ground, because it absorbs the part of the ground wave energy when the ground wave is propagating, and it's following the Earth curvature. So the conductivity of the surface of the ground, of the terrain, is what matters in this case. And when the conductivity is increased, this results in less dissipation of the energy. So ground waves are more effective over the water, for example, surface, because the conductivity of water is larger than of the ground. What are the main applications of these ground waves? Well, first of all, these are some long-range communications used in military sphere, for example, with the submarines, with the ships, and of course, it depends largely on the frequency, and it gives us opportunity to travel larger distances, which is very useful for the military equipment. Of course, it's also used for long-wave radio communications in the upper range of these frequencies, and even for AM broadcast, which is now obsolete way of broadcasting, but some part of this AM broadcast the upper part of the spectrum, sorry, the lower part of this AM broadcast spectrum belongs to the ground waves. So AM signals actually travel as the ground wave and as a sky wave. We will learn about it a bit later, what is sky wave. Let us just assume that they travel in both ways, depending on the certain range of this AM broadcast. And here one of the interesting facts about this, the lowest possible frequency used for communications. This relates to extra low frequency range, which is up to 30 Hertz only. This is extremely low frequency for communications. Like we learned in our example with the far field. Do you remember when we assumed that the free space loss could be negative, and we concluded that it couldn't because the conditions are not right? So we concerned something like this, extremely low frequency, back in this lecture. And the wavelength of this frequency is 10,000 kilometers long. This is enormously large wavelength. But it can theoretically reach any place on Earth. So we can communicate, of course, with certain limitations and under certain conditions, but it makes it possible to communicate with the submarines anywhere in the Earth, on the Earth, even with deeply submerged submarines. So we shouldn't take a risk to let submarines get to the shallow waters in order to receive the signal. The submarine can stay deeply submerged in a safe place to not be detected by the radars, but still obtain some signal. And here's a story that in 1960s there was a project by US Navy officials who wanted to make it possible, make such communications possible. So in order to make it possible, they had an ambitious plan. They wanted to bury a gigantic grid of cables under roughly 41% of the state of Wisconsin in order to turn its bedrock into the world's largest radio antenna. So they wanted to create an antenna which supposed to be 10,000 kilometers long or 6,000 miles long. Can you imagine? And they would make it as a buried wire which is grounded at both endpoints, and the current which is going to be excited, the signal, the driving current of the signal to be transmitted was assumed to take different paths under the ground, under the terrain, in the bedrock. So we would have this circuit, this closed circuit, going through this wire, this large wire, and circling back through the terrain, through the bedrock, again to the other pole of this wire. And thus it would produce the varying magnetic wave, which would produce the varying electric wave, and further on we would have the electromagnetic wave produced this way. That was very ambitious project, but it didn't. It wasn't realized. It was cancelled because the expenses were too high, and also there are some neighborhoods which were not happy with such enormous construction going on close to their homes, so it was cancelled. However, this project was revived in some smaller scale in 90s, and it was around 14 miles long, like shown here. and this grid of cables wasn't that big, that long, right? But it's still allowed to communicate even with the submarines in the Mediterranean. So this project was realized, but to a lesser extent. Here it how it looked like, how it would look like. You can see that even deeply submerged submarines would receive this signal, and the same diagram can be shown here as well. So this is how this extremely low frequency was utilized for some military communications. All right, so let's get further to the sky waves. What are the sky waves? Sky waves has a range of 3 to 30 megahertz, and these are actually reflected or refracted signals from the Earth ionosphere. As we learned in the previous lecture, what happens there, that the phase velocity becomes larger than the speed of light in vacuum, and this makes them refract downwards, be refracted from the ionosphere, and this would allow us to communicate over the horizon. So if we don't have a direct line of sight, we can send this signal under a certain angle to the ionosphere in space and just expect it to be refracted or reflected from the ionosphere and reach the other side, the receiving side. Why does it happen? Because ionosphere is full of electrically charged particles. It's actually a plasma, and it produces this effect with a certain frequency range. Sky waves can reach intercontinental distances even. And sometimes even AM broadcasting stations use this skywave propagation. That is why this effect can be observed when the receiver could obtain a signal from very distant radio station, somewhere very, very far away, with a better signal quality and strength than some nearer transmitter. And while AM broadcasting doesn't usually rely on the sky waves, right? This effect can be observed by this. So we can receive some signal which are very distant, very far away, larger than our near signal. All right. And the last way of propagating is the so-called tropospheric scatter. It's called tropospheric because it takes place in the troposphere of the Earth atmosphere, and it allows to communicate up to 500 kilometers long distances. This effect takes place for the frequency range of from 300 MHz to 30 GHz. But the optimum frequency is 2 GHz. So 2 GHz is scattered in the most effective way. So actually, this is our microwave range. So theoretically, it could be used for microwave communications. So why wasn't it used? The signal is randomly scattered as it passes through the upper layers of the troposphere. So it loses significant amount of power. And actually, these propagation losses are that high that only 1/1,000,000th of the transmit power is available at the receiver. So this is some sporadic event, and conditions vary with the atmospheric conditions. And we receive just a small fraction of our signal. That would require us to have large antennas, large parabolic antennas with very high gain. Of course, we could communicate to large distances, but we couldn't preserve the signal at a normal level all the most of the time, and we would lose most of the signal. The losses are too high. So that is why this type of propagation is not frequently used for the communications, and it was discovered like in 50s, I guess, and used for some time for military communications because the distance of communications was very large. But then it was replaced by the satellite communications in the 70s, and now it is not used at all. So this was our final mode of propagation. 4 main modes: line of sight, ground wave, sky wave, and tropospheric scatter. Not mentioning the non-line of sight because this is a subsection of the line of sight, but with a higher diffraction losses. So this concludes our big section on signal propagation, and I hope that it made it clear for you of how the signal propagates in space, and I hope that you could use this knowledge in your professional life, in your career, and just for your interest. I hope that it was also interacting, it was entertaining for you, and please do not forget to take a quiz, take a test to test your knowledge. And again, I wish you Merry Christmas, and we will see you again on next Wednesday, and finally we will start with the antennas, another subject in this video series. Goodbye.